Okay, so we begin Chapter 12 today, and we're reviewing some Algebra 2 topics, one particular topic. Today we're going to be solving linear equations, systems of linear equations using two different methods, substitution and elimination. And these will be systems in two variables, and then eventually we'll branch out and do systems in three variables using these same methods. Really, the system that you're given will determine typically what method you use, and we'll talk about that as we go through these problems. Your instructions, I just took them out of your book. You're to solve each system. If the system has no solution, write inconsistent, and we'll look at how do we know when a system does not have a solution. Well, on number 19, even though you're not wrong, depending on if you choose substitution, that would be okay, but I'm going to choose elimination because I noticed that if I multiply the top equation by 3, I will set up eliminating the y variable with addition. So elimination says pick a variable to cancel, and you can do that in a couple of ways. I'm going to just multiply the top equation by 3, and I'll just write that in up above. Everything in the top equation multiplied by 3. And since I've essentially replaced this blue equation with the red, I'm just going to mark this one out so that it won't be confusing. And so the operation, that means add or subtract, the operation that's going to be required to eliminate y will be addition. So I'm just going to put a little plus sign here as a reminder that I've got to add like terms all the way across. 15 plus 2x is 17x. And we've accomplished our goal. We have eliminated the y variable because they cancel. And then over here, 63 plus negative 12 is 51. So we solve for x here by dividing by 17, and I went ahead and gave you the answer. We get x is 3. Well, the solution to a system is obviously solving for both variables, and to be a true solution, the variables when they plug in for the respective, or the numbers when they plug in for the respective variables have to make both equations true. If it makes one of the equations true but not the other, then it's not really a true solution of the system. So once you find a variable like we have here, we found x, then you can plug that value in for that variable in either equation. Doesn't matter which. So I'm just going to go to the bottom equation here, and I'm going to let x be 3. And we're going to solve for x. I'm going to basically subtract 6 from both sides. And divide by 3 on both sides. And your answer will be written like this, as an ordered pair. Something that sometimes comes up that is maybe a little bit confusing when variables other than x and y are used in a system like a and b or r and s, then you just write your ordered pair using, just think alphabetically. R comes before S, C comes before D, and you just write your ordered pair in that way. Okay, let's try this one. Do you see a possibility? Which method would you pick? And if so, help me out. How would you go about solving this system? Anything stand out to you? John? Okay, and you're trying to eliminate which variable here? Okay. Okay, does it really matter if you do 3 or negative 3? No. What will it determine, though? I mean, if I leave it like it is and I use positive 3, then what is it going to take to eliminate x? I'm going to have to subtract. Some people prefer to always set up addition. And that would mean, in this case, I would multiply by -3. At this point, you're advanced students. I'm going to let you choose. I'm not going to mandate that you always do a certain thing. You pick whatever you feel comfortable with. Okay? So I'm just going to leave it, like John said, I'm going to leave it as +3, knowing that when I get to the elimination part, I'm going to have to subtract. All right, so the top equation multiplied by 5, 15x minus 30y is 10. And the bottom equation multiplied by 3, 15x plus 12y equals 3. And as a reminder, I'm going to put subtraction here. I got to subtract every term as we move across, left to right. X's cancel. So -30 minus 12 is -42y. And 10 minus 3 is 7. And when I divide by -42, it starts off like this. But of course, this reduces, 7 goes into both of these, and right in denominator, it becomes -1/6. Okay, which checks out. And now I plug -1/6 in for either one of those y's, but although there's not a wrong choice here, there sometimes is a better choice. And I think you see which one's the better choice, right? Plugging into the top, because that makes easy math. So 3x minus 6 times -1/6 equals 2. 3x, and this becomes +1 plus 1. 3x equals 1, x equals 1/3, which checks out. Okay, do you have any questions so far? We haven't looked at a substitution example yet, so let's do substitution here. Substitution says pick a variable in either equation and solve for it. Substitution works best if I have a variable in an equation that has a coefficient of 1. And if so, that's the variable that I should pick to solve for. So of the 4 choices, the 2 x's and the 2 y's, the best choice is to solve the top equation for y. That's the easiest. I can do that in one step. Now, substitution also says after you've solved for a variable, then replace that variable in the other equation. So I'm going to come down here, and in place of the y in the second equation, I'm going to put -2x plus 1. And we'll be solving for x. And we get a weird answer. Because what happens to the x terms? They cancel. And what is left is not true. 2 does not equal 3. So this is a clue. Whenever you get to this point, the variable cancels, and you're left with a false statement. This is sometimes known as no solution. But we're told in our instructions, if it is a no solution, we're going to say that it's inconsistent. AKA, there is no solution to this system. Okay, but you got a little taste of how substitution works. And they don't really specify in your instructions which method to use, so I'm going to leave it up to you, but understand that certain systems lend themselves more towards substitution, others lend themselves more, they work easier with elimination. It's kind of up to you to decide which one is which. Okay, what do you think about this problem? Which method would you pick? Cody? Substitution? Okay, we can do that. And which variable would you solve for? So x on the top, and you would get negative 2y plus 4. And what does substitution also involve after this? Okay, replace the x in the denominator, so 2 times negative 2y plus 4 plus 4y equals 8. Negative 4y plus 8 plus 4y equals 8. Well, here we have one of those weird situations again where the variable drops out. And we're left with a true statement. Just the opposite of what we had in the previous problem. So whenever we're left with a true statement, this is called being dependent. And what this means is if we graphed these two lines, basically it's really two different equations that represent the same line. Can you see it? What if I take the top equation and multiply by 2 all the way across? I'm going to have the bottom equation. So whenever this happens, when you have a system, it looks like on the outset that it's two separate equations, but when we look closer, it's actually the same equation twice. Whenever that happens, you'll always call your solution dependent. And another way of saying that, it's not all real numbers. It is, though, it's all ordered pairs that would fall on this line if it were graphed. Okay, so one way of saying our solution would be, since Cody went ahead and solved this for x, we could say our solution is all xy such that x is this. And then y would be any output from that. We will call that, I'm just going to explain it in this way so you'll know what we're talking about. Any output that results, we can use any number we want. Another way of saying that, it could be all real numbers. And I'm not going to have you explain it like this on your test or your quiz, but I just wanted you to see that it's not just any number we want. It is, however, any ordered pair that would fall on this line if it were graphed. Any xy on that particular line. Okay? So we've looked at one solution. We call that consistent. There is an x, there's a y. We've looked at no solutions. We call that inconsistent. And then we've looked at really an infinite number of solutions, any ordered pair that happens to fall on the line, and that's called dependent. All right, so let's try this one, number 35. Can you see a better way? These are fractions, a little bit harder to deal with. What do you think, John? Multiply by 3. Yeah, you could. You're not wrong. You really don't have a wrong choice, but sometimes there's a better choice. I'd still have a fraction here. I better do it this way because they can't see it. I'd still have a fraction. So if you're trying to get rid of fractions, that wouldn't really help. Yeah. 2. And I agree, that would take care of this one, but you'd still have 2/3 here. So if you're trying to get rid of fractions, if that's your goal to turn this into, you could do 12 on the top, and what would that turn the top into? If I multiply by 12 all the way across, Lily, what would that give me on the top equation? Okay? And now I'm working on the bottom. Which would be easier to set up elimination for? Would it be X or would it be Y? Which would be easier to turn? Would it be easier to turn 1/4 X into 6X with multiplication, or 2/3 Y into 4Y with multiplication? Can you think of something that we can multiply or divide 4 into to give us 6X? 4 into something equals 6. Okay, what if I multiply by 24 all the way across? 24 times, or you could do negative, like we said earlier, you could have done negative 24. So 24 times 1/4 X is 6X. And what is 24 times negative 2/3? Okay, and it would be minus 16Y. And then over here it would just be negative 24. So now we've set up elimination of X with subtraction. And so you just have to keep in mind, remember 4 minus negative 16 is really 4 plus 16. That's 20Y. And 30 minus negative 24, that's really plus, is 60. So who got Y as 3? Okay. So which equation do you think it would be better to plug 3 into for Y? Top or bottom? And you can use these as well once you've already changed them from their non-fraction form. So you want to go with the top? 6X plus 12 is 36. 6X is 24. X is 4. Who was able to get that? Great. Any questions? So I tried to pull out a variety of the problems that you're going to see. Now let's jump to 3-variable systems. So I'm going to use this one using substitution, and then the next one we'll do elimination. Okay, well, substitution says the same thing. It works the same way when it was 2 variables. We need to pick a variable to solve for. And our choice, hopefully, is one of the variables that has a coefficient of 1. That's the best. So you really have 2 options. We could solve for X on the top. We could solve for Z on the bottom. Really doesn't matter. I'm just going to go ahead and solve for X on the top. So when I solve for X, I get X equals Y plus 6. So again, substitution says once you solve for a variable, then you replace that variable. But now we're going to have to replace it. We don't have an X in the bottom equation, but if we did, we'd have to replace it there as well. So what I'm going to do here is I'm going to replace the X in the bottom with Y plus 6. And I get 2Y plus 12 minus 3Z is 16. And 2Y minus 3Z equals 4. Okay, everybody good so far? All right, so what I can do now, this is kind of a combination. We started off with substitution. Now I'm going to go elimination, and I'm going to set these up because they look like they match up pretty perfectly. They already have 2y that will cancel with subtraction. So I'm going to take this bottom equation and this result of substitution, and I'm going to solve, in this case, it's going to be solving for z using elimination. And that's pretty simple. I just have to subtract them. So 1 minus negative 3z, that's positive 4z. And 4 minus 4 is 0. So z is 0. So the answer to these three variable systems will be called an ordered triple. And just put your numbers in alphabetic order. So we know what z is. And now I've got some choices. I can use what z is, and I can come back up here and I can replace z with either one of these. Just put 0 in for z. And let's just go with the middle. You wouldn't be wrong if you went with the end. If I let z be 0, then what's x? Everybody see that? X is 8. 2x equals 16. X is 8. Now, how do you think I will find y? Well, you have some options. Give me one of those options. Well, if you wanted to, you could go up to the top, and now that you know what x is, you could let x be 8. And what does that make y? If x is 8, you subtract 8 from both sides. Yeah, negative y is negative 2, so positive y would be positive 2. When we found z is 0, I just chose this one. I put z in, or 0 in for z, and it made 2x minus 0 equals 16. So that means x has to be 8. Yeah.
Could you just finish that equation? 2y minus...
Sure. Yeah, that's why I was saying you have several options here. Any questions? So I wanted you to get a look at substitution with three variables, even though substitution in three variables usually starts with substitution, but then it eventually becomes elimination. Okay, so let's take a look at this one, and we're going to do pure elimination on this. So elimination with three equations, three variables, you really need to survey the problem first and get a good idea of a variable that looks like would be good to eliminate right off the bat. And again, there's not necessarily a bad choice, but a lot of times there is a better choice. So what do you think? Okay, I would probably agree. I would say that the y variable looks like the easiest to start off eliminating initially. So here's what we're going to do. We'll call this equation 1, equation 2, equation 3. I'm going to pair up equations 1 and 2. Just put them together as their own separate, you can call it a system. And then I'm going to pair up another two of these equations. Really doesn't matter what I choose, but I mean, I've only got so many possibilities. I'm going to go ahead and do equations 2 and 3. With the thought that I'm going to eliminate the same variable, and Cody said, and I agreed with him, that the y variable looks like the easiest of the three to eliminate right off the bat. So it's a very important point that when you create these two pairs, you eliminate the same variable within each pair. Big, huge point. Okay, so if I'm going to eliminate y, then I need to multiply the bottom equation by 2. And I'll just do a different color just to make this stand out. So this bottom equation on the left side here, I'm going to multiply every term by 2. So 4x plus 2y plus 2z equals 8. And now I'm going to mark out this old red equation since I've replaced it. I'm just going to mark it out so it won't be confusing. And what will it take now to eliminate y? Well, I need to add or subtract. I need to add. So let's put a little plus sign as a reminder. 1 plus 4 is 5x. The y's eliminate. 3 plus 2 is 5z. And 7 plus 8 is 15. Okay, now I'm going to jump over here to this other pair, and I'm also going to eliminate y. To make that happen, we can either, you have a choice, you can multiply negative 2 all the way across, or positive 2, depending on if you want to add or subtract. I think I'll just do negative 2. I'm going to multiply negative 2 all the way across. So negative 4x minus 2y minus 2z is equal to negative 8. So let's mark this one out. And I can eliminate y here with addition. Negative 4 plus negative 3 is negative 7x. The y's cancel. Negative 2 plus negative 2 is negative 4z. And negative 8 plus negative 10 is negative 18. Okay, so at this point, we're in familiar territory. We're going to take these two equations that both have x and z in them, and we're going to put them together and do elimination. Okay, so 5x plus 5z is 15. Negative 7x minus 4z is negative 18. So I probably need to go to a new slide. What variable would you go about eliminating and how? Let me just go to a new slide. 5x plus 5z is 15. And what's that bottom equation? Okay, so Lily, what do you think? Which variable and how? Okay. Top by 4 by 5. Okay, we'll go with that. So multiply the top by 4 all the way across. 20x plus 20z is 60. And on the bottom by 5, negative 35x minus 20z. Let's see, what is that, 90? 18 times 5? Negative 90. Okay, and addition is going to be required to eliminate z. So 20 plus negative 35 is negative 15x. 60 plus negative 90 is negative 30. So we got our first variable of the ordered triple, x is 2. Now that I've found x, it's like I'm going to go back through my work. When I find one variable, I need an equation that has two variables. So it doesn't matter which one I pick, but I'm going to stay away from a negative. I'm just going to go with this top equation, 5x plus 5z, and I'm going to let x be 2 so that I can find out what z is. 5 times 2 plus 5z is 15. 5z is 5. I'm going to be subtracting 10 from both sides. Z is 1. Okay, I found two variables, and now I need to go all the way back to the beginning, replace x with 2, z with 1, and again, it doesn't matter which one I pick to find y. I think I'm going to go with the middle. We said x is 2, and we said z is 1. using this middle equation, we're going to find y. So 4 plus 1 is 5. So we're going to be subtracting 5 from both sides, and so we get y is negative 1. So this is the way your answer will be written. Ordered triple. Any questions so far? I'm going to set you up on a couple of word problems, and then we'll skip this one. I think we've seen enough of these. You've got a word problem that's similar to this. Let's just take a look. To me, this is the big reason why we learn to do elimination and substitution with systems. It's to solve these real-life application type problems. So we have this movie theater, and they charge $9 for adults, $7 for senior citizens. 325 people paid. The total amount of money collected was $2,495. How many were adults who paid? How many were seniors? So the rule of thumb is, in this case, we're looking for two different solutions, two different answers. So let a variable represent each of these two groups. So it doesn't matter what you choose, but tell me what your variables represent. So I'm just going to let x represent the number of adults. So whatever the question is that is being asked of you, that will determine what your variables represent. The variables should answer the question. And I'm going to just let y be the number of seniors. Okay, and with those two variables, we're going to make two equations. One of the equations will be based on the number of people that came. So we're told that a total of 325 people paid. Well, if x is the number of adults and y is the number of seniors, the two of those together should be 325. So I have a number of people who attended equation. And then I'm going to have an equation that will deal with the amount of money that was collected. And if they charge $9 for every adult that attended, 9 times x. And they charge $7 for every senior citizen that attended, 7 times the number of senior citizens. And the total amount of money that was collected, $2,495. So we have a system. And how do we solve it? What do you think is the best way? Substitution, elimination. I'll let you pick. I'll give you a minute or two. And if you need a calculator, you can grab it. See if you can come up with how many adults paid and how many seniors paid. Just out of curiosity, how many of you used elimination here? Okay, who did substitution? So, okay. How many adults did you end up with? 110? Okay, so there were 110 paying adults. And what about the seniors? 215? How many of you were able to get that correct? Very good. Any questions? John, I saw where yours is just a little bit off. Probably just a little arithmetic mistake. Any questions? Probably not, because you guys all did that really well. We'll probably just have time to set this one up. This is going to be a 3-variable system because the ultimate question is how many are there of each kind of seat, and there's 3 different kinds of seats. So that tells me I'm going to have 3 variables, and anytime I set up 3 variables, I'm going to have 3 equations. All right, so as we read through this application problem, the theater is divided up into orchestra, main, and balcony. All right, so you need a variable to represent the number of seats in each section. And I'm just going to say X will be my orchestra, probably more specific number in the orchestra. Y will be the number in the main section. And Z will be the number in the balcony. Okay, and typically in these word problems, there will be separate sentences that will lead you toward an equation. We need an equation that represents the total number of seats in the theater. And there's how many? Okay, so Cody, what would that equation look like? Okay, so we have a total number of seats equation. And there's typically an equation that deals with money, total amount of money collected. So let's see, Stacy, what would that equation look like? That's okay. Okay, so I'll just do 50x. Okay. All right. Very good. So now we come down to this sentence. If all of the main and balcony seats are sold, but only half of the orchestra seats are sold, the gross revenue is this. So I'm looking for ideas on how we can turn this sentence into an equation. John. Anybody put something down for that? Yeah. Only half of the orchestra you could, or you could do 1/2 times 50x, which is the same thing. And then what else? Okay. All right. That's fine. You would get the same thing, 25x. Okay. Probably not going to be able to finish this one, but I just wanted you to get it set up. If you understand how to do substitution or elimination, if you did substitution, you would take one of the variables probably in the top, solve for it. Let's say you solve for x. If you solve the top equation for x, change color here, you would have x equals negative y minus z plus 500. And then you would replace the x in the other two equations with this. Okay. So I've kind of led you toward how to get to the solution. Typically, just coming up with the system is the challenge. Most people, once they get the system, they're pretty good at solving. Do you have any questions? We're pretty close to the end. Any questions? I gave you the slide with the assignment already, so we'll check these out tomorrow.